Um, Hi everyone. We can start with the next session. So the next session we will have a couple of presentations. Yesterday we had an Arathon, and we had 5 teams that participated. The teams were from the students from different universities that are attending. They are with us here today. The 5 teams, each team had 5 to 6 people, and they worked on data that was collected over the on the Era platform. So one of the data was the TV white space MIMO, right? And then the second one is the data collected over the backhaul links, and then the mobile UE with the COTS radio over the bus. So we had a kind of a competition. We had 2 teams selected that will be presenting their results today with us. So the first one that worked on the TV white space massive MIMO data team. They basically worked on the data, and then they generated some insights that they will share with us here. So Eduardo, yeah.
Just waiting for. I invite my colleagues from the team. So hello everyone. So hopefully you are not too asleep at this time. So yeah, basically what we did is like a weather-based cellular KPI prediction framework. So we worked 7 people. This is a photo. And basically, our goal with this data was try to characterize what happens with the weather when the weather is changing in the radio, let's say, side. So we wanted to study which indicators were potentially affected by the weather and how. So the radio propagation and possibly the performance on the UE and the base station. And based on that, try to gather some possible prediction models. So first of all, I wanted to emphasize that one day data is not enough, okay? But I don't know if you are film lovers, but there is this kind of films like, for example, Crash or Babel. I don't know if you know that film, where a single story is, let's say, told from a different points of view. So we work in that way that we let the data to speak for us and to tell us a story. So basically we did some data analysis, like time series visualization, and let the data tells us the story, what happened, okay? So we will start with the weather story. What happened with the weather on that day? So this is the graph where we are showing the humidity, the temperature, and the pressure. And the first thing that you can notice is, there. No. There. Yeah, okay. There is some gap. Something happened between 11 and 12 that we don't know. There is just some gap. So yeah, it becomes to be interesting, right? So, and the humidity, you can see certain pattern, it's going up and down, and the temperature is doing some kind of oscillations, but the values, the range of values is not changing much. The same applies for the pressure. What happens with the wind and the rain? Okay, so wind, it kind of fluctuates, but it stays, let's say, in 2 levels. And the interesting thing is the rain. So we can see that it was raining in, let's say, 4 periods during the day. So I just mark in green here. So it was let's say, more appreciable rain here. Let's say heavy rain here, heavy rain here, heavy rain here, and light rain here, okay? So that was pretty much the story of the weather. Now, the second story is the base station story. What happened with the base station during the day? So basically, we checked the main performance, like the data rate, and we gather, for example, 3 different data rates: the MIMO, the per user, and spectral efficiency. And if you can see, visually, both these 3 KPIs are basically doing the same thing. So we can, let's say, concentrate that the knowledge is you just need to study, for example, the spectral efficiency. And what happened when it started raining? So you see that there is a very high degradation here. So maybe, but we don't know, it has something to do with the rain. So every time it's raining, there is some mess, okay? Then I will continue with the third story, the user story.
All right, so after what we get to know about the weather, what the weather was like, and also what's going on at the base station, so we would like to show you some story or some data from the UE side. And first of all, we like to show you the spatial distribution of the base station and the UEs to kind of give you a sense of where they are. So, all right, I cannot really. Okay, so the yellow dot here shows the base station, and then we used 3 UEs in the data set. So that is, there's a closest one, and then there's a middle one, and then the farthest one is the dairy farm. So we would like to show you later on, this spatial distribution of these UEs, what will be the impact of it. So first of all, we'd like to show you, this is the received gain / power versus we have, humidity here, but we have talked about so many weather factors. Here we would like to show you very important one, which is humidity. So what you can see here on the left is the received gain and / power, and on the right is the humidity. So the x-axis is time of the day. And what you can see is that here on the blue curve, that is first of all, probably the orange curve, which shows the received power, and you can see very clear variation during the day. And if you compare that orange curve with the right plot, which is humidity, you can see a very clear correlation between the two, and that is when the rain happens, and then the humidity during the day just increases. So what happens is the channel quality gets bad. So what happens is that you would have much lower received power, and later it resumes back. And then with one more information is about the receiver gain, and that is, since we're using MIMO, so what happens is that it adaptively tries to accommodate this loss. So that's why we have this increasing gain and then lower it down later on. So now we have the 4 plots. Don't be scared about it. So what it is about is essentially we have 3 same plots at the 3 UEs that we just previously described, and then the lower bottom one is the humidity, which is the same figure as the last slide. So what we're trying to show you here is there is some spatial impact we actually also observed. So we found out that this one, the dairy farm, which is the furthest one from the base station, what it happens is that it shows a more clearer pattern or correlation with the humidity, whereas the upper left one, which is the closest one, you can see it's not much correlated. So what it means is that we can see there's a spatial impact on the received power with humidity. So with that, I would like to switch to my next teammate, and then he will talk more about it.
Hello. So I will talk about the latency that the users were experiencing during that time. So during the rain time, you can see in this area, the latency was very high because this is a heavy rain region. At this point, the rain was very high and the latencies were very high, and similarly, this region was also a heavy rain time. And we have experienced more latency here. And in this region, during this 2 p.m. to 4 p.m., the rain was light and the latency was not that much. But after we observed that there is bad latency experienced in all UEs, and especially in the UE, this is the blue one UE. The blue UE is actually the closest UE to the base station, but still it experienced more latency as compared to other UEs, although they were the further one. The reason for that is, if you look here, for the closed UE, during this time we observed a very spike in power loss. the received signal loses power in this region. So this tells us that for the channel between the base station and the closest UE was bad during this time. Why it was bad? It can be because of any weather condition. It can be any other condition. But the data that we were given with, it's not evident enough why this data was bad and how it impacted the latency of first UE in this region. So obviously we had a gap here in the data that I want to explain. So gap was about when after the heavy rain, the system stopped working and the sensors were not working anymore, and that's what the team told me. They removed the values from here and the random values that we generated during this region. And also, if you observe that first the rain started accumulated, and then there's a constant rain, it means the rain stopped here, then there's again heavy rain here. And after that, if we observe that this is a distorted data, but we cannot see a very high steep slope to the next point. It means that during this region, the rain was stopped, but although the rain was stopped, but the sensors were not working, so we omitted that data, and this is the gap in data that created that disruption in all the graphs. And in the accomplishments, if we can see, the first thing is what we observed. The weather matters, the rain matters, and the weather metric that affected most of the 5G system was the humidity and the rain. During the rain, the 5G system was, the latency of the system, the signal strength and the channel was affected very badly. And we observed that with the, channel was distorted most with the humidity. And on the other side, the user, this also tells us that, like we also observed, in the UE that was farthest from the base station, that was affected most by the weather. So it tells us that when there is rain, it should be taken care of, like the edge systems that are deployed from farther, they should be managed better, because they can lose their connectivity and everything. And on the other side, from the base station, the spectral efficiency matter, and the other thing is a gap that is anomaly in the system. So that can be fixed with the maintenance stuff. So right now, the problem here was we only had the data for 1 day. And that was not enough data to generate the correlation between the weather and the performance that we observed in 5G system. Although we saw some correlation with the humidity and other factors, but if we want to compare these metrics very closely with the performance of the system, we need more data. So more data means we will build a better prediction model, and we can see that how different weather metrics are affecting the 5G system. Like right now, we only discovered that humidity was affecting, but maybe the temperature is also affecting that, and we were not observing that much. And the same is with the pressure one. So, yeah. Thank you.
Yeah, thank you so much. Thank you. Yeah, looks like there are like really interesting problems here. Yeah, thank you so much. Since we are over time, if anybody has any questions, they can directly talk to them. Yeah, but I mean, just in general, like just with 1 day of data and then like spending few hours, like there were like new findings and like the data analysis, which shows that, yeah, I mean the overall the data on the Era testbed, right? How much potential it has, and if we are giving like if we provide like more data, right, that it will be even more helpful to study the dynamics of the channel and the weather conditions. Yeah, thank you. Yeah, the next team. Yeah, the next team actually worked on the CARTS UE radio, which is mobile. It's deployed on the Cyride bus in Ames, and the data was collected from that UE, and the team basically studied it, and they will share their findings with us.
Can you help me set up the PPT? Was it there? Oh, okay, it's there. Okay. Which one is the light?
Actually, it's better to use this.
No. Yeah, if you want to. Okay, thank you everyone. I hope I won't take much of your time. So this is the results from our first first ever hackathon, probably, I think, for us. Yeah, yeah. So the goal of our analysis is just simply to answer what is the coverage performance of the base station deployed at the Ara testbed. And again, I want to preface that this analysis was done with time limitations. And we were stuck at a problem at some time, and we did not do all the analysis that we wanted to do. But yeah, this is the methodology. We use a data shared to us by Sarat. Thank you. He just went and gave us like at that time, at the morning, and it contains timestamp, GPS coordinates, RSRP, RSRQ, SINR, PCI, and the alphanumeric cell name. And there's total about 500,000 rows after clean, which is with 2 seconds granularity of the data, means that we collected about 12 days of data. And as the first pass of the analysis, we mapped the data as a heat map. So it's the usual thing, bin the data into squares, 50 by 50 meters, take the average for RSRP and RSRQ, or the median for the SINR as the representative of that squares in the heat map. And yeah, this picture shows the where they deployed the mobile UE, which is in front of this bus, and this is how it looks like. I also don't know how they do it, but it's like magic, I guess. And yeah, we just tried to map it at the first time, but somehow the data is somewhere in China. And this is what Sarat like warned us first, like they may have we may have a problem with the GPS coordinates. Seems like I thought that it will be like 10 meters or 20 meters, but it's somehow in China. And but then we just try to look at the data, and we noticed that the longitude is positive, and we know that the western hemisphere should be negative in longitude. So we just try to flip the sign. Close but no cigars. At least it's near Nevada. Nevada City, not Nevada State, Nevada City, Iowa. And yeah, it's closer now. So we go back to the data again. So we now know like the problem is actually the data, not our codes. And so Omkar, one of our team member, noticed that the digits after the decimal point, it's like 0.3 and this is 0.00. They never go above 60. So then we kind of, okay, let's try to assume that the data is in DMS, degree minute seconds system, rather than actual floating point. So we just separate the digits after decimal point and divide it by 60. And that's the function that we use. And voila, it works. And that's how we get this data now. And yeah, this is the mean RSRP, the map with the heat map of the mean RSRP. And we see that the bus covers a large area, and they have only one bus that equates with the UE, but the bus is reused on different routes. So this is a multi-days data. And we see a coverage gap here, and my friend will discuss that. And the signal received in this location is actually comes from this base station, and like this faraway base station from agronomy farm base station is actually received right at the edge of this data, as this map. And this is the same plots with higher RSRQ. And my commentary on this is like the RSRQ seems to be like high on most areas, but when we map the SINR, there are some spotty areas there. So there's some kind of like futures work that we can try to compare SINR and RSRQ in like how they actually indicates quality of the data. And next.
Okay, this is a very quick analysis. So I was trying to figure out why there is no coverage in this region. That's strange because it's connecting to the same base station, Wilson base station on top. So what I did is I went ahead and checked OpenStreetMaps for the 3D profile, and I figured out one of the possible reasons could be because of the buildings in this region, but it still doesn't answer why we are getting coverage on the northern side. Then I went to another database where they were talking about the height of the terrain, and we can see that there is a depreciation in this region, while it goes back to the same level. So it takes a dip, the terrain level, and then it goes back to the same level. So that could be the reason why we are getting coverage in that region. Now, also, since we had the GPS coordinate, what we did was we don't have the base station PCI, the information of where the PCI is directed towards. We just plotted the spatial distribution over the map, and we kind of can get a sense of which in which direction the PCIs are oriented towards. So that is what I'm showing in the following couple of slides. Probably one of the things that comments that we would have is that we need to have a better density of the data collection. What I mean by that is we need to go through all the roads to get an idea of how the PCIs are located. So in this plot, you can see that PCI 5 and PCI 4 doesn't have much of data collected towards the direction. So the reason could be because the routes were very well designed, and we need to cover more routes. This is also a similar plot that talks the same point. Thank you.
And later, after fixing the location problems, we decided to have some measurements, some results, and try to really understand this data. Basically, the first thing that we started as a key to evaluate it is the RSRP, RSRQ, and SINR. These basically SINR shows the signal to interference noise ratio, reference signal, power, received power, and RSRQ. Now let's see what is with the data that we have. What is the performance of each of these PCIs? Is this performance? Because first we saw that only one frequency is used from the base station. It's a 100 megahertz channel. And if you see from the frequency perspective, actually RSRP, it's at a good value. It's at a normal value. RSRQ and SINR, 15 dB. It can go better at 20 dB, but it's not bad, 15 dB. Now, is this distribution the same for all of the PCIs? Is the question.
Press it again.
Mm-hmm. And we see that the distribution, it is not the same for all of the PCIs. There is a problem with the colors. I couldn't fix the colors for all of the PCIs. For example, the base station, the PCI 3, 4, and 5 that are nearby this base station, maybe it's the reason because the bus was going near to the base station, they have the highest SINR, highest RSRP, and RSRQ. For example, in terms of SINR, PCI 3 and PCI 4, they are around 16, 19 dB a medium, but the PCI 2 and PCI 0 and PCI 11, they are pretty much lower. What is the reason why these PCIs they don't have the same performance? Based on our initial results, we see that PCI 2 and PCI 3, they are PCIs that are operating between this base station. So it's base station Coors Farm and base station Wilson Hall site. The region between the PCIs that are located in the region between these two base stations, they are suffering in terms of SINR, RSRP, and RSRQ. There is from the information that we have, each of the base stations, they are using 3 sectors, and within those 3 sectors, they are performing 5G new radio. This can be, we don't know how much user-specific beamforming they are performing. Is it only SSB-based beamforming or more like PMI or table-based beamforming? But the conclusion is the PCIs that are assigned, or the users that are assigned passing between this base station, they have the lowest PCI because only one channel is used here, and there is a high possibility that these PCIs probably they are exposed to co-channel interference. Moreover, another interesting thing that, as Mohammed mentioned, if you see the data, the measurements that are taken from the PCI 2, 3, and 4, there is connection, low, no connection, connection, low, no connection. So it looks like the base station, this base station and this base station, they are competing with each other. The user is competing to which base station to connect with. There is created an SINR threshold when, as far as you go below this threshold, for example, PCI 7 is connected to this base station that is pretty far. So this partial region, it is under an SINR threshold, and as far as this received signal, it does not exceed the user, it is not able to access. But even this, when the user comes here, even it is far away from base station 7, if you've seen the distance, similar distance between this base station and this base station, it just directly goes to the base stations, to this base station. So it looks like for the region, when for the center campus, when we have multiple base stations, there is a potential of exposure against co-channel interference, and a better radio resource allocation. In terms of the frequency, it is, I think the only hope it is in terms of a frequency, but we have all the users, they have a 100 megahertz channel. In terms of the power, I don't know if it is any possible, any potential solution, because power depends on most of parameters. It is the channel there. Can we have a full control of it? Simple split of the frequency can be a solution, and to see if these PCI they have same results or not. Thank you.
Yeah, thank you so much. Let's have a round of applause for. Yeah, thank you so much. And with this, actually, this shows that with few hours, like 5-6 hours of this Arathon, actually, we were able to identify some of the issues, like by the participants, which actually helped us, for example, the gap analysis and the GPS issues, right, that we are able to identify it, and then we would be able to resolve it. And it also shows, like, with collaboration, like using the testbed, performing the experiments, using the data, right, together we can do really exciting work on error testbed and work on exciting problems as well. With that, we will go to our next fireside chat that Hongwei will lead.